as an advanced innovation engineer in the mass industrial automation, and then he has worked as a senior design for automated railway crossing in the signaling Sydney, and currently he's working in ResMed Sydney as an embedded software engineer. So he has a well background on embedded hardware as well as embedded firmware design. So I will warmly welcome Engineer Pradeepa Senanayake to conduct the talk. Thank you.
Okay. Thank you very much for that introduction, sir. So yeah, and thank you for inviting me to deliver this presentation. So welcome everyone. I can't see your faces, but yeah, there are many who joined this meeting, and I welcome you all. So in this presentation, my main idea is to not go in detail about any subsection in embedded systems engineering, because we have so many things to discuss in embedded systems engineering, and since the audience is mainly of undergraduates of third year and final year, I decided to make this presentation as a general presentation so that you all can relate and you all can decide whether this is what you want to do in your career. And if you have questions, you can always ask us, and also then you'll have a sort of a rough idea what this field is all about when you in like next couple of years when you go into the industry. Oops. Okay, all right. So first of all, a disclaimer. The content of this presentation is purely my personal view and is not representative of my past or present professional affiliations. Why I say that is because at the moment I'm working at ResMed, and any material that I say and any definitions that I give are not the view of my company or any other companies that I have represented. So this is purely my personal experience. So I don't think that I need to go through this slide. So first of all, I'd like to define what is an embedded system. This is, I think, since you are learning embedded systems, you might have come across this question many times, and it's always a pretty tough question for me. But it's for me, like, an embedded system is something which is developed with the purpose of achieving a specific set of use cases. So this is not a definition that I see in many books, but there are many related definitions. And if you ask for, if Dr. Sudhir somehow asks for in a question, ask what is an embedded system, don't write this, because this might not be the correct textbook definition. And I would like to, I would invite you to like challenge this idea, or just come up with any alternative definitions if you feel like, because this is just what I feel an embedded system is from my experience so far. So now from this, actually, I just like to ask a question from the audience or from the listeners. I don't know how to call you guys, like from y'all. How many embedded systems are there in the world? I know it's kind of a stupid question per se, because no one would be counting number of embedded systems, but just to have a rough idea of what we're talking about here, if there's anyone who would like to like unmute yourself and give an answer as to how many embedded systems you feel that there is. And please don't Google, because I did the same.
Approximately 1 trillion.
1 trillion. Okay, that's a pretty good guess, actually. Maybe that's the correct answer. Who knows? Anyone else? Okay, so since I got an answer, let's move on. So yeah, based on Google, it says like 10 billion in USA alone and 100 billion worldwide. So that is what Google says. And the main idea is to like see like how many, like the number of devices is ridiculously high these days. most of the time these numbers are calculated based on the microcontroller production, so things like that, because it's pretty hard to crack these numbers. But the fact is that we can see embedded systems almost anywhere in the world at the moment. And how many embedded systems do you think that there is in a modern car? Not in a very old car, but a modern car. How many do you think there is? Anyone can answer, just that I know that you guys are there.
10.
10. Okay, that's a reasonable guess. Any other?
100.
100. Okay, so we have two extremes, 10 and 100. So yeah, what Google says is it's somewhere around 50. Actually, these things I just Googled them so that we can have some numbers to start the presentation with. Yes, 50 embedded systems. That's what it says. Because as I said, some people might think it's just one, because it's just one control unit. But based on the way that we usually architecture these things in embedded world, we have so many modular systems. Like we have separate embedded systems for the steering control, and there's separate one for infotainment, separate one for braking systems, and all these things combined in one particular thing called a ECU. So there can be so many. So there are battery controllers now. So yes, I think 50 could be something. It could be a reasonable number, and 10 is also a really good guess, and even 100 in a like a pretty sophisticated Tesla, maybe 100 might be a good guess. So yeah, no one is wrong. I just wanted to have to check, like, to get some feedback from you. Okay, so let's keep this slide. Right, so I'm just going to like talk about few embedded systems categories. As I said, I'm not going to dive into any detail, but I just want to give you a rough idea of what this is. So one of the basic embedded system is the consumer electronics. These can be found anywhere. I'm sure that all of you own at least one consumer electronics device. So the cameras, refrigerators, microwaves, the washing machines, the any radio, any what is this home assistant system. So all these things are consumer electronics and are embedded systems, because they they are designed with the focus of uh, having like a very specific use case, or a set of specific use cases, related specific use cases. So that's why it's going back to that definition. So the washing machine is basically it is to wash clothes, but in order to support that functionality, the control system and everything is developed with that mindset. And the camera is something similar. So everything else is something similar. And then wearable tech is also something that is actually picking up still. I think because of the maybe the battery technologies, it's still lagging a little bit, but still it's picking up. So especially the wearable, the watches. So this is, I think, a Garmin watch, and these type of sensors that can be connected to your shoes are now being sold. I've seen so many places that these things are being sold. So because when you have sensors connected to different places, the feedback that those sensors can receive are different. So because of that, the decisions that these devices can, so the data points that these devices can provide for some other system which to generate uh, uh, data science ideas will be different. So because of that, now we have like sensors like this that we can just wear on our shoes and go for a run. And like it sometimes detects the wind speed even. So yeah, this is also something, actually even MAS does this these days. Like they have some wearable clothes, some clothes that detects the movements in the muscles, and it just, and also it sends it can also, I think, detect the composition of sweat, so that it know how, whether the workouts are effective and things like that. And then automotive and transport, so this is a ECU, and these things are just infotainment. So this is something that actually I worked on. So the railway level crossing sensors, that you might not see these things in Sri Lanka because we don't have automatic railway crossings, but in most of the other countries these are used. So this particular thing is a induction based uh, wheel sensor. So when a train passes this, it checks that it can detect the direction and whether there's any train presence and also the speed of the train. And from this information, it just provides a signal so that the railway crossings can operate. And then the medical industry. So this is the ResMed's couple of devices. This is a very popular device. This is a ventilator. So we design a lot of ventilators. And this is a sleep therapy providing device. So this is where I'm working at the moment. I'm designing this particular device. And this is a pacemaker. So when it comes to medical and automotive, for example, even a rail crossing sensors and ECUs, these are very safely critical. So if this did not, if somehow this failed, then it means that the level crossing would not work, and that could end up being catastrophic. So because of that, there are many standards and there are many specific design methodologies that we need to follow when it comes to designing such stuff. Same goes with the medical devices, especially devices like ventilators and even pacemakers. They have very strict guidelines when it comes to design, especially like let's say ventilators, because there have been a lot of talk about ventilators in last couple of months. So actually in like the first, maybe in June, July period, there have been a lot of discussion around designing ventilators. So one of the arguments is that the standardization of these equipment is very high, because the moment that one of these equipment fail, that means someone's going to die. So this is very critical, and because of that, we need to have so many redundant systems. We need to have alarming capabilities. There are many, like every and single equipment, every and single thing that we have in a circuit has a redundant component. So, and also the software testing and the way that we write the software is also completely different from every other device. Like there are different classes of software. For example, this one is a sleep therapy device that if this fails, no one's gonna die. Basically, no one's gonna, it can hurt a person, but it's not gonna kill a person. But if this fails, so because of that, this says it's a class C device, and the software guidelines are and the hardware guidelines are for class C devices, class C medical devices, whereas this is a class B device where a failure would be a catastrophic failure. So in those cases, the 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 way that we approach those products and the way that we develop those products are completely different. And the military grade is the other extreme, like, because if you have ever ordered electronic components, you need to select whether, like, because usually they have separate devices for separate things. If your device is a consumer electronics, your temperature ranges are different, and if your device is for military purpose, then your temperature ranges, the operating conditions are completely different. And also this needs to be highly precision. The precision is very important, and there has been, like, I can remember back when I was in Sri Lanka, I used to play around with the NRF, RF, the radio frequency module, and we learned that that module is being cloned in China. Like they just clone the IC and they sort of manufacture counterfeit products, and some of those ICs are going into aeronautical, like military as well as aerospace engineering products. So there has been a lot of talk about how to prevent such things from happening, because yeah, these are very critical things. So this is another class of embedded systems. And another one is agriculture, which is something really fun and something very good, like something very satisfying, because like you are basically helping people, especially the medical and agriculture industries are very fulfilling when you start working in those industries. Like, so I think in Sri Lanka we have like AI Grow project that is doing some smart farming, and here in Australia there are like so many agriculture related startups and companies which invest heavily in precision farming and like greenhouse and things like that. So precision farming is one of the areas that is focused, like heavily focused these days, because of how everything is happening in the world, and like because the amount of water these things the agriculture consumes is pretty high. So because of, in order to have tackle those problems, the agriculture industry is also starting to catch up in electronics field, and these are not that safety critical, etc. But however, like there'll be so many sensors in this agriculture industry. So because of that, the power consumption of each of these sensors is going to be a critical concern. So therefore, now we discuss like so many types of embedded systems, and these are not by any mean like the only set of categories. So these are some things that I have experience with, and some things that everyone can relate to, hence I added them into the slides. So there can be many others, and I'm sure that some of you might be thinking, oh, there's this category and there's that other category as well. And yeah, you all are correct, like if you're thinking that way, because these are not the only set of embedded systems categories that are available in the world. So therefore, my definition of an embedded system can be reduced into this. So we have set of inputs, and we have a processor, and we have certain outputs. The inputs can be sensors and outputs are actuators, and this whole system is what I call as an embedded system, because throughout the last 7 years that I have been in the industry, everything that I worked on has this structure, and this is exactly what an embedded system is. This is the most simple way to describe what an embedded system is from my point of view. So I'll just share some of my personal experience from last 7 years on what I've been doing, and if you go into the industry, what you could be doing. So uh, I was involved in designing scanners in Sri Lanka. So this particular device has had a processor and contact image sensors, LDRs, and some magnetic swipe readers as sensors. So this information was processed using few processors manufactured by Cypress Semiconductors and also ST Microelectronics, and there was some developed by a manufacturer called IMX. Uh, uh, they are now I think previously they were also known as Freescale, and now they were acquired by a company called NXP. So those processors used to capture this information, and then from this information we derived certain binary data that we transmitted over USB to a computer, and also the LDR. It was LDR. These LDRs were used to uh, find out where the the document is in the scanner. It's a different type of scanner. I'm not going to go into detail of what scanner it is, because I'm not sure that I'm allowed to. So, and then because from using these position sensors, it controls a motor control. And so with this in mind, when we approached the design, it was realized that we cannot achieve the data rate that we required from the contact image sensor all the way to the PC. So because of that, the FPGAs, or the field programmable gate arrays, were used, and there were like different types of devices. Some use microcontrollers, whereas some use microprocessors. So we had like several classes of devices. Some use FPGAs with microcontrollers, some use FPGAs with microprocessors in order to transfer that image data into a PC or to to a website. So this is basically a high level design. Like we have a microcontroller. I've really simplified these designs. These are far more complex than what you see here. I just don't want to overwhelm you guys with so many sensors and so many things. I just want to try my best to make this as concise and simple as possible. So this MCU means microcontrol unit, and we have image sensor, which is connected to both microcontrol unit and the FPGA, and the FPGA is providing some signals like some clock signal pulses to the image sensors, so that image sensors will provide necessary image data to microcontroller, which is directly sent over this symbol. I guess you know it's a USB, so this is sent over USB, and there's like a separate something like a DMA. If you know what DMA is, a direct memory access. It's DMA means like when you want to have a high speed data stream from one end to another end. If you use the processor to do that, then you are going to waste a lot of processor cycles to copy that data from A to B. So instead of using the process cycle, what you can do is you can configure something called a direct memory access module to transfer all these into the whatever the output. So those things were used, and there are many other sensors that connect to microcontroller, and FPGA is also used to control stepper motors to control where the document is, because in this particular scanner the document is moving, and the scanner, the image sense element stays stationary. If you have any questions, please ask. And I'm sorry, I don't have another screen, so because of that, I wouldn't see if anyone's like raising hand or anything. So if you have any question, just unmute yourself and you can just ask. And then there's this another class of scanners that I've worked on, which instead of using the microcontroller, we use the microprocessor. And in this microprocessor, it ran embedded Linux, and on embedded Linux there was a web server, and from Ethernet connection we can connect to that web server, and through the web server we can control all these modules. In that case, we like designed Linux drivers and things like that in order to interface the FPGA, the image sensors, and the motors, and all the other sensors. Like I can remember one of the first tasks that I did when I joined Zone 24/7 was writing a LED driver, a kernel mode LED driver, and yeah, just to blink some LEDs in one of these boards. So yeah, that was one of the first tasks that I did as an embedded engineer. So this one level crossing sensor, I worked in a company called Aldridge Railway, and that's where we designed these level crossing sensors. So this is also a very interesting piece of hardware and software. So we had an inductive sensor, so basically two coils, and those coils are connected to an oscillator, and that oscillator is providing a PWM signal to the processor. So whenever a train passes that inductors, the pulsed current, the magnetic pulse is it there's an interference because of the material is ferrous. So when the train wheel passes the sensor, the PWM signal gets changed, and we detect that through the processor, and then using that information we can calculate the speed of the train, the direction of travel, and everything. So, and then that information is transmitted wirelessly to an actuator, which operates the railway crossing. I think this is currently installed somewhere in Sydney. So yeah, I worked like just 6 months in the latter stage. Actually, I worked on this project even when I was in Sri Lanka. So, and then when I moved to Australia, I worked full time on this project until we finished this. So it was also a very interesting project. We used a special Texas Instruments safety related microcontroller. So as I said, like the automotive industry is completely different. Like this is basically a scanner is a consumer device. If a scanner failed, it's going to be an inconvenience, but that's the best that it can do. But if a level crossing sensor fails, then the inconvenience is not just an inconvenience, it could lead to a catastrophe. So because of that, the processor selection and everything is different. So in this case, the processor has something called safety. It is safety, but since it's from Texas Instruments, they call it safety. And so they have like very specialized hardware built in the processor to make sure that the processors, all the peripherals inside the processor is always working accordingly, like working to the specification. If there's any issue, it would just flag, and then we have like separate circuits which are independent of the processor, which can handle data cases. Basically, we'll close the gates, I think. So it will close the gates and it will just send signals to the whoever is looking after, whoever is maintaining that sensor.
Pradeep,
So
sorry for the
yes,
interrupting. Yeah, it's
yeah,
good that because in the embedded system course also we talked about the real-time embedded system and the critical embedded systems as well. So it would be great, like as you do, like you can emphasis on the how they will be different from a normal embedded system. So you can
yes,
the way
okay,
you talk is perfectly fine, and you can always keep that in mind when you talk about. Okay?
yeah, yeah,
That's
okay, yeah, that's pretty good. Like, uh, like mainly, okay, okay, I heard some noise. Okay, so yeah, that's pretty good actually. It's good that those things are covered in the course as well. Like, so in this particular case, like, uh, the main requirements were around the microcontroller selection, and like there's something called like, if I going a little bit in depth, like, so like usually when we have an embedded systems that are like separate, like software architectures, we have like one giant while loop which does everything. So we have like a while one loop, and inside that loop we have all our code, and which gets executed over and over again. So that is one of the most common ways that we implement firmware in a microcontroller. But when it comes to the safety related microcontrollers, they have something called a diagnostic period. So usually in every couple of seconds, I can't exactly remember what the number of seconds are. So after a certain number of seconds, we have something called a diagnostic mode, which tests whether every peripheral is working. Like it injects a fault into our memory, and it checks whether our memory detection units can pick that up. So those things are already done in the microcontroller unit. So these are like these are most of these things are now, we don't need to code them into our system, but there are like specific peripherals, just like SPI or just like RTC modules. There are specific peripherals that does that helps us do this work. Like we just need to configure them in the initialization. Even initialization is completely different. Like when we initialize, before before we execute our code, we test each and every peripheral, we test each and every sensor, and then once everything works, we switch into the code. So there are many things like that. That's a separate talk altogether, to be honest. So I will not go into like in detail, but if that if those things are needed, then maybe we can have a separate session some other time. So yeah, so I was talking about this, and so basically, if I talk about the high level design, we have a microcontroller and we have our inductive sensors. So we actually this sensor is just providing us a PWM signal, and we are also providing it something like a off on signal, because this is an oscillator and there's a very complex electronic circuit here in the inductive sensor, and then it gives us a PWM signal, and the microcontroller is reading this signal to check whether there's any variations, and from those variations we detect whether there's a train. And then if there is a train, like if we detected a train, we are going to transmit that. And here also I can remember we had like 2 radio modules for redundancy. So we had like, because if one failed, then the railway crossing is like it's not gonna work. If one fail, then we are not going like railway crossing, which is if it's located somewhere else, might not get the receive the signal. So we transmit in both. So because of that, at least one would be successful. So, and this same system, like with now this rail crossing can also be directly connected to this system, or there is something which uh, doesn't like directly connect to, like for example, if you think like without this rail crossing, this this part will be just the sensor. So it is connected to the rail rail line, and then once it detects, it transmits to another system which does the rail crossing, the rail indicators and things like that. So if something failed here, then it will definitely it will like activate all the safety systems in this microcontroller. So that this is a very, it took like 5 years to complete this design, as I can remember, with so many iterations and so many iterations in software. So yeah, so that is one other thing in the level crossing sensor. The device that I'm working on at the moment is a sleep therapy device, and I'm not allowed to share like the internal details of the sleep therapy device, but I will uh, talk about the rough idea how it's done. So we have a microcontroller and we have flow sensors and pressure sensors. So this is the main 2 sensors that we have, a flow sensor and a pressure sensor. And from the readings of the flow and pressure, there is like a, a huge library which does digital signal processing to find out breathing patterns, to find out any anomalies in breathing, and that can take uh, actions on that can detect whether we have any issues related to breathing and any issues related to sleeping. So when we sleep, like if there is any breathing disorder, then we might not know that we have that breathing disorder, but our brains wouldn't get enough oxygen, and our brains would keep on waking us up, so that we'll have many other sleep complications in the later stage. In like we will feel very tired during the days of things like that. So the device that we manufacture provides therapy so that the people can sleep properly. So we use flow sensor and pressure sensor data, and in the processor, in this particular device we use a real-time operating system, because it's it's another design paradigm, to be honest. It's like it's easier than writing everything on bare metal and much more predictable. And yeah, so because of that, we use a real-time operating system, and then using the flow sensor and pressure sensor readings, we generate the controller parameters that we need to send to the motor controller, so that we can again control the pressure of this of the air going into the our sleep therapy device. So, and also this has some wireless data transmission, so that we can monitor patients in the field and to see whether there's any issues and to make sure that the doctors can uh, change the therapy to as per their diagnosis. So that is the sleep therapy device. So I those are like three different areas that I worked on. There are many other, but I just selected those three because they kind of cover like few extremes that I was fortunate enough to be involved in. And when it comes to main design options of all the designs that I talked about, so there's something called a bare metal implementations. The bare metal implementation means we can write code that runs on the microcontroller itself. Like instead of running on top of an operating system or anything. For example, you have seen like so many so many applications that we have in our laptops, in our computers. They work on an operating system. So there's another class that is running directly on the microcontroller, and they are called bare metal implementation. So that is something that we use in like if we if our if our design is very small, and if it's like straightforward to implement, most of the time we go for bare metal implementation. And also there's another paradigm called implementing the features using a real-time operating systems, where we have like real-time operating systems. There are many in the industry at the moment. One of the free ones is called FreeRTOS. Currently, it's gaining popularity a lot because Amazon recently purchased FreeRTOS, and now they're supporting it in the ecosystem as well. So because of that, the real-time operating system is also gaining a lot of traction. And then the next one is the embedded Linux platforms. So we can develop our features as applications in these embedded Linux platforms, and that is also widely used, and it has been there forever. And like if your design is somewhat complex, then like for example, if you need to run a web server and many other things in your device, then it's a good call to go for something like embedded Linux. But embedded Linux platforms and real-time operating systems, if you compare, embedded Linux platforms are not, you can't use those things for safety critical applications because they are not predictable, whereas real-time operating systems are predictable. So there are like many design options when it comes to firmware design in these areas, in these devices. So now we come to the crust of the presentation actually. So everything that I talk so far is mainly about what the embedded systems are and how we design and what are the design paradigms behind these designs. So things like that. They are mainly about the applications, and some of some of you might feel overwhelmed with like so many names and so many stuff that's going on that I've been blabbering last 30-40 minutes. But if you really think about what you need to improve, it's not much, to be honest. So I'm just going to share like some of my personal experience with you from here on. So how did I learn what I do? So this is something that I've been doing from maybe from second year onwards or third year onwards maybe. Uh, so main skills that you need to improve if you're willing to work in embedded systems industry is one is firmware development. Because yes, we all are electrical and electronics engineers, but when it comes to a device, after you design the circuit, the brain of the design is in the software. So we need to write the firmware, otherwise you will just have a dead device. If you have like bricked phones, then that is what just electronics would bring you. So you can have the most sophisticated electronic design and have a dumb firmware design and then have a failed product. So the easiest is to learn the firmware development. Like you need to learn languages such as C or C++ thoroughly. Learning C++ thoroughly is very hard, but learning C thoroughly is actually pretty easy. So because it's such a small language, so you can learn it very fast. And also electronics. When I talk about electronics, you don't need to know like the most complex IC designs or things like that when you if you are in embedded systems. For example, if there are final year students and if you are taking the electronics specialization courses, so those things are we hardly do designs like that. Those are that's an amazing subject by the way, but so if you have like if you feel like this is what the embedded systems industry is doing, no, that's not what we do. Basic knowledge on electronics means we are like connecting microcontrollers into different sensors that you need to know how to filter out noise using a capacitor, how a transistor works, and what happens when we connect a resistor to this and that. So things like simple electronics. That's why I say like basic knowledge on electronics. I mean, as an electrical and electronics engineer, a basic knowledge on electronics doesn't mean connecting an LED and switching it on. So when that basic knowledge means like at least going to like using an op amp, a transistor in a basic setting. So you don't need to design a receiver or wireless receiver all by yourself. No, that is not what we are after. And also, if the FPGAs are separate field, I think there are many companies in Sri Lanka which does a lot of really good work with FPGAs, and it's also another very interesting area. I've also worked on FPGA designs for like 3 years. That's also a really interesting area, but it's another specialization that if you really like to go for, learn about FPGAs. I mean, you might not learn everything from the uni, but that's where you need to like read and learn about those things. Microcontroller internals. When it comes to microcontroller internals, there's no point of studying the ARM assembly code uh, and by hearting them. So what the industry wants is a person who understands what an interrupt is and when an interrupt occurs, what happens, or what is a DMA and how does DMA helps our designs, things like that. And then comes the support languages like Python, because we don't usually use Python at this stage. We don't usually use Python for firmware development, but when it comes to using like when it comes to testing devices, we extensively use Python. And when I say testing, like that is a complete different topic actually. Since I'm in medical devices field these days, the amount of time that we spend on testing or writing tests for our devices is more than the time that we actually spend on writing production code or developing production software, because that it is that important writing tests. So 90% of the tests that we write are written in Python, and because and as a supporting language, Python is amazing. It's very easy to use, so it's always a nice language to learn, and nice or very good experience if you can, if very good skill if you can uh, gain that. And the ability to debug device and ability to learn new technology. So embedded systems industry is always changing, and we get new ICs, we get new firmware, we get new communication packages. For example, when I joined the industry, we were learning Bluetooth 2, and that was a big thing. And now it's I think Bluetooth 5 or 6. I think 5 is definitely there, and I'm not sure whether 6 is here. And I can remember back when it was USB 2, and now I think it's USB-C. So it's USB 3. I I managed to work in USB 3, USB 2, and USB 1, and I could not work on USB-C devices at all. So things evolve and things change. So because of that, as an embedded systems engineer, you need to be able to learn new technologies whenever the technology becomes available to you. So next thing, how to learn. So learning C, as I said, is the easiest. So this is the book for C. If you want to learn C, get this book and read it. I think maybe it is there in the library, should be there in the library. So this was written by Kernighan and Ritchie. They are the two developers who develop C language, and they have written the book about C, and this has everything about C language. So if you read this, you know C basically. Learning microcontrollers. This is where you need to experiment. So these are two amazing development boards that you can just buy for very low cost. So I think this is like $14. So that is maybe like, let's say $20. It was 14 back then, I can remember. So it was like 3,000 rupees. So for 3,000 rupees, you get all the peripherals. For example, the sleep therapy device that is in the current market has this IC. So this is the brain of that device. So if you basically get this development board, you should be able to develop a sleep therapy device. This is all you need as a microcontroller. And if you use some device like this and learn how to interface with different I2C, SPI, and then different buttons, LEDs, and whatnot, like you can connect anything here. This has even USB, so you can even develop USB applications on here, and you can just experiment about that and read the data sheet, extend, like try to read the data sheet and learn what is there. Because if you learn how to read the data sheet, then you can learn about any microcontroller, you can learn about any IC, any sensor. So it's very important that you read those data sheets. This is a Texas Instruments one called Stellaris. I think they have discontinued this now. It's a Tiva C or something. It's a different, but still looks the same. It's called Texas Instrument Launchpads. These are also these are also very cheap, and I think they ship to Sri Lanka as well. I bought both these when I was in Sri Lanka. It was very cheap back then. So this is how I learned C. Actually, this is just my personal experience. Okay, so this is how I learned C++. I read this book called C++ Primer, and I still read this book, to be honest, every day, and I still learn new things. So it's very hard to finish learning C++, but if you read like 5 chapters of this book, you are good to go. Next three is basically up to experimentation. Learning Python. I have never used a book to learn Python. It's basically experimentation and ability to debug devices. If you play around with these two development boards, you would learn how to debug devices. Learning USB, Bluetooth, and any other communication protocols would definitely give you an edge over anyone else. Because I mean, 90% of you would know how to write a basic program, and there'll be someone who knows how to write a Bluetooth application. So that person has an edge. So that's where you need to spend some time and learn about those Bluetooth or USB or any other technologies like that or protocols like that, so that when you come into the industry, you'll be better. Yeah, so I just wanted to share with you an image. So this is an image that I've taken after I cleaned my room. So these are some of the stuff that I have accumulated. This is the discovery board that I showed you, the STM, and the Stellaris launchpads, many other Hercules. This is the railway level crossing sensors main board, and this is the development board. This is the IC, and this is the development board for that IC. So, and this is a FPGA Altera D0 Nano. So, and this is a USB 3 development kit, a Raspberry Pi, an Arduino. I hate Arduinos, but still it's there because I wanted to know what it is. And Beagle Bone Black. So this is like the things that I played with when I was at uni. So that, and also I like after some within, I think even when I was at Zone 24/7, I used to like play with all these development boards so that I will be updated. And these are two routers that I broke, and this is my second year third the embedded system design project, signal generator. It still works, by the way, and it can generate sinusoidal signals and stuff. I mean, before I moved to Australia, I switched this on and checked, and it still works. So yeah, so this is, you need to invest time if you want to gain anything in your life. So basically, it's same for embedded systems, but you need to know what you need to learn. So that is what the responsibility of the university, like it will teach you what you need to know, and then it's up to you to go and figure out what you want to do and how to learn it. So my uh, idea was to provide you with enough keywords and enough guidance to let you guys know where to seek information from, and we are always there to help you if you need anything. The last thing I would like to tell you is to have a blog and write things, like if you are really serious about what you're doing, just share with the rest of the world, and not for any not to get any validation. Like, don't expect people to add likes or comments on your post, but just for your personal benefit. So for example, this is a blog that I started when I was in uni, and to this date I maintain it. It's just I just I sometimes don't have time to write, but still I try to contribute. So I today, like when I was designing this presentation, I checked it and I found this post. This was in February 2013. So this was when I was in final year at university. So these things I bought when I was in final year. There are some very embarrassing videos as well. So yeah, see, this is after see this one. This I posted this after buying MSV 430, and that's when I decided to to have a blog. And it says it's just $4.5, so it's something like, back then it was like 500 rupees. So I'm sure that we waste more money on other stuff. So these are things that you can do, and this blog has helped me a lot in getting so many jobs actually. So, and now I have a separate website that I try to keep updated. So it's pretty good if when you have something like that, so that it just encourages you to learn. And when you that is even now, that is the way that I keep myself updated with the new technologies. I just try it out myself and then write down what I find on the blogs. But and sometimes even these things help other people. Like, there are many places where people have come back to me and ask for help in their projects. People from different countries and who are going through different issues, and have checked uh, these websites and have come back to me and asked for questions. And it's pretty good if you can do things like that, and that will help you in the process. Finally, the best practices in this embedded systems is, like, there are many standards. For example, there's a standard called MISRA C, which says how to write programs in C. And there are device classes, as I said, class B, C devices based on different requirements in medical industry, which are governed by these medical standards, and railway signaling is governed by these railway standards. So there are so many standards. If when you are like when you have an idea to design a software or design a device, you need to always learn about these standards. And then testing is a completely different topic. We can spend days discussing about this, like how do unit test embedded devices, what is known as test driven development, how to write tests before you write a code, what is a behavior driven development. So these things I've learned, like, after I started working, to be honest, all these things. and the modular designs and platform architectures. So that means instead of having everything in one circuit, you'll have like different modules, so that you can have plug in different modules and have one platform. Then just remove stuff. It's like your hardware also becomes something like software. You can update it. Key take-home messages: experiment with tech. As I said, experiment and learn to develop firmware libraries instead of using the firmware libraries. It's very easy to use a firmware library when you want to like interface some sensor. You can just download the library and just interface it, or you can learn to develop one. When you learn that, you learn a lot of other knowledge as well. Resist, just get it done mentally. Like, because I'm talking about you being an undergraduate, because when you're an undergraduate, if you have the mentality of just get it done, then you wouldn't learn the correct way of getting it done. When you come to industry, sometimes just get it done is the mentality that you need. But when you are an undergraduate, it's a different process. Start a blog and write something, read technical and non-technical books. Never hesitate to reach out to us if you need any help. Definitely. So there have been many individuals who reached out to us and we've helped. So if any one of you need any help whatsoever for your final year projects, for any of your hobby projects, for anything, you can always reach out to us and we are available to help. You can talk to us, like send a private message to us, doesn't matter. If there's any way that we can help, we will definitely help. There's even though you might not realize, there's a huge community looking out for you and looking after you. So if you need anything, you just need to reach out, and we'll be there and we'll help you out. So I just wanted to like simplify the embedded architectures and things like that. So it's Albert Einstein says genius is making complex ideas simple and not making simple ideas complex. So embedded industries is actually a simple industry if you really think about it. There's not much going on. It's just that we somehow make it complex. So it's just, as I said, it's just you have some sensors, you have a processor, you use those sensors and use the processor to generate some meaningful outputs from those sensor data. That's what embedded industry is all about. So thank you all, and good luck to your studies and for your future. And as I said, if you need any help, please reach out in at any time, and we'll try our best to help you. Thank you very much. Okay, so I'm not sure what happens now. Is there any IET representative or anyone who's does anyone have any questions? If there's no questions, then I think we can wind up. So I'll give like 5 minutes. I'll just say 5 minutes if you have any questions.
Hi, great presentation there, Pradeep. Just a question on why do you hate Arduino?
Why do I hate Arduino? Yeah, it's mainly because of the overhead that it has on the designs, and then the fact that it takes the engineers, the uh, whoever the undergraduate students far away from the actual hardware. It just takes them to a different abstraction, because what we see now is that there are so many people who claim that they know a lot of they know about a lot of technologies, and when we interview them, what we realize is that they lack the foundations, the skill to develop a library, the skill to debug a library. 90% of the chance is that when we are in the industry and when we are working, we usually get issues that are very low level. And if you are an Arduino Pro and you have not used other like bare metal devices where you would go close to the processor and debug those things, then it becomes very hard for you in the industry when you face with such issue. So that's my main issue when it comes to Arduino. And to this day, in last 7 years, I have never worked with any industrial application that used Arduino. We use Arduino for prototyping, true. That is just the first stage, and that never went into production from my experience. I'm not going to generalize this. There may be products that use Arduino. I'm not going to generalize this, but I have never experienced, and even today, I have never heard anyone using Arduino. So that is the main reason why I don't like Arduinos. Arduinos are good for year 12, year 10, 11, 12 students to learn about electronics, but not for undergraduates to do their projects or anything. They need to, like, if that's a proof of concept, a hackathon, definitely go for Arduino. But when it comes to learning about embedded systems, and if you get yourself like in this Arduino business, then you lose you lose a lot. You lose a lot. That's the main reason.
Great answer. Thank you.
No worries. Oh, there are some chats. Give me a second. Okay. Why do you? Okay. Will it be worth buying a FPGA board? Okay, this is an interesting question actually. So Primash, uh, it's definitely worth it, buying an FPGA board if you're willing to learn FPGAs, because that is something that it's pretty hard for you to learn if you don't have something to play with. So in my personal experience, that's the main reason that I invested my money on an FPGA development board, because I'm not representing any company, but I purchased Altera D0 Nano. So I'll just type it here. Like, it was back then, it was very cheap. Not actually, comparatively, it was expensive, I think. So if you, maybe there are ports in uni, I'm not sure, but if there are people who would like to learn, maybe I can ask alumni to check whether we can contribute some boards to the department or do something like that. But if you can, definitely, if you have the capacity to purchase and if you think that's a good investment, I would say you can do a lot. Any other questions? And I understand that embedded systems is not everyone's piece of cake. Some people hate embedded systems and some people hate electronics. I don't like power systems simply because I don't understand power. So if it might not be everyone's piece of cake, but this is like that's the main idea of this presentation anyway, so that you all know what you're getting into. So if you love it, you are going to enjoy it for the rest of your life. But easier for me to say, no, I wouldn't say rest of your life, but it has been an amazing journey for me so far. So any other questions? All right, so since there's no other questions, I think we can wind up here. Okay, what is the difference between PLC and embedded system? Okay, so PLC is the programmable logic. This is the programmable logic control. I think what you mean is what we use in industrial applications, right? Like in machines, machine controls and stuff. So usually PLCs are very general, and you have like there are different standards of PLCs. So the things that I've used, at least the ones that I used when I was in MAS, we used a little bit. I'm not an expert in PLC, but from what I understood is they are like already manufactured embedded devices that we connect together for to achieve another purpose. For example, there are motor controllers you connect, and then there's this sensor you connect, and then when you hook that up, there's this interface, everything well defined. You just need to, I'm oversimplifying definitely, but this is what it is, right? So you just connect the inputs and to the outputs of the next one. The coding and everything is already done for you. So that is how it works. That's what my understanding is. However, when it comes to embedded systems, it is like, for example, let's assume you need to do an image processing on the go, and for things like that, the PLCs are not gonna work, because it's not gonna give you that flexibility as well as that power. But at the same time, that might not be the case now. That's my experience. So that is the main difference that I see in embedded systems and PLCs. PLCs are like a highly standard and different paradigm altogether. So that the main purpose is industrial automation. But embedded systems, for example, you can have a PLC in your camera. So that is, PLCs are for industrial automation, whereas embedded systems is just the general idea. I hope I answered the question. I hope I understood it correctly. Okay, no worries. So is there any other question? I'll give 1 minute if someone's typing.
Hello, good evening, guys. Are there any more questions before we wind up the session?
Okay, there's one message. Give me a sec. What is the importance or connection of USB protocols and other peripherals to the system? Uh, I'm not sure that I understand what is the importance of connection. What is the importance of USB protocols and other peripherals to the systems? To the maybe what you're asking is what is the importance of USB protocols and other peripherals to embedded systems? If that is how I interpret the question, but if not, please feel free to have a chat, or you can ask, you can just unmute yourself, ask. Okay, cool. Yeah, so uh, USB USB is like the data communication protocol. So as you know, so if you want to send something out, then there's this particular way that we need to format that data, and then there is this particular, like for example, when it comes to serial data, there's you need to send, like when we are sending data, we are sending a start character, and then we are sending data in this specific rate to the other entity. So when it comes to USB, there is a specific way that we need to send data, and that mechanism is defined in what you call a USB protocol. So that is what the importance is. Like, we need to follow that protocol if you want to have two sides communicate using the same mechanism. It's like talking in English. So when I'm talking English, if you want to know how to understand that, you need to talk, you need to understand English. So that English is the protocol. So when you say the importance of USB protocol, that means the importance of English in communication. So importance of any language in communication, it's to understand each other. And other peripherals, that means like let's say I2C, RTC, they have their own place. For example, if it's something called RTC, RTC means real-time clock. The importance of real-time clock peripheral to an embedded system is that peripheral provides the actual clocking mechanism. That's how you have time in your watches, things like that. So that is where the real-time clocks come in. So different peripherals have their own. Bluetooth has its own importance. So that is that is how like different protocols and peripherals becomes how they become important to systems. I hope if that I'm not sure whether I answered the question correctly, but that's how I understood the question. If is Raspberry Pi really used in industry, or is Raspberry Pi is not even see, I have seen Raspberry Pis in like billboards. I've personally seen them in billboards, like, but I'm not going to say billboards are industry. I have never seen a Raspberry Pi used in industry. But Raspberry, if you really read about Raspberry Pi, why Raspberry Pi was introduced is so that the United Kingdom, the people, the kids in UK will get into programming. It's for STEM. You know, the STEM is science, some science, technology, engineering, mathematics, something like that. So STEM, in order to promote the STEM education among kids. So, and then the hobby market, the hobby industry has taken that up and has has used it for different purpose, for different hobby projects. But if you really want to learn like embedded Linux or use a single board computer, proper uh, uh, a proper one would be a Beagle Bone Black, because that has like I'm going to type it out. So Beagle Bone Black. So this has the open hardware and open software. So you can install any Linux kernel. You get the schematics, you get the data sheets and everything. So you can customize it the way you want. So yeah. So I think Raspberry Pi is, I can say it's not even, it's, yeah, it's academic only. I can say that. How important is to learn the integration of embedded systems on Linux systems for undergraduates? I would say it's not as important as learning bare metal implementations. So it's definitely not a must have, because it takes time to learn Linux systems and in embedded Linux, the kernel drivers, etc. It takes time. It's just it's about like you need to learn it properly. Like if you are learning about Linux, then you need to learn C language, things like that. So if you are really into embedded system, the first thing that you need to learn is C language. Learn it, and then just play with some microcontrollers. Just learn how to toggle pins, how to configure an LED, how to configure an interrupt, use a push button, and then which triggers an interrupt, which triggers an LED, things like that. And then like use some peripherals like UART peripheral, universal synchronous UART, that receiver transmitter module. So use those peripherals to communicate with the PC and just print some things. So there are many tutorials that you can find to do things like that. So that would be number one. Once that's done, if you have time, definitely go for it. Learn Linux. I don't think that I knew Linux when I was in university. When I can remember like when I went to uni, when I went to working at SON, I didn't know what a bootloader is. I mean, so don't, I mean, you don't need to know everything, right? You just need to know the basics. That's why I say like when we see undergraduates coming into industry claiming that they know everything, we know that like that's very tricky thing. Like if you know everything, great, but if you don't know, the person in the interview panel would know that you don't know. So because person in the interview panel would be someone who's a seasoned engineer, so he would have experienced all that you have in the CV. So yeah, so it's up to you. So learn something and try to learn it properly. Is assembly used in firmware development industry? Yes, it is used in firmware development industry, but not that much. There are, like, for example, when we are debugging, uh, I, I use I need to read assembly usually every couple of months at least, because sometimes when we debug a code, there are debug some firmware, we need to go through assembly instructions to figure out what the processor is doing. So there are cases where we do that, and I have written assembly language for ARM systems a little bit of very simple routines. Sometimes we need to write, but in order to do that, you don't need to learn assembly or anything like it. I don't think that spending time in learning assembly, it's okay to learn basic things, to how to like do a move, how to load a register into a memory, things like that. But apart from that, you don't need to do it. But I back then when I was in university, we did the project purely using assembly, and that was one of the best projects ever, and that has helped me a lot. And even to this day, I use that knowledge to read and write assembly. I think that's enough. If you have that, at the moment we use PIC 18F or 16F or something, and we had to write everything in assembly. It was Dr. Janaka's uh, uh, subject. I'm not sure whether he does it now. Yeah.
Any more questions? Well, then, on behalf of Dr. Sudhir and Aratna and the IT on-campus University of Peradeniya, I would be glad to extend a very sincere vote of thanks to our guest speaker of the event, engineer Mr. Pradeepa Senanayake, for taking the time out of your busy schedule to conduct this session. And I'm so grateful for the effort and time you took to share your knowledge and experiences with us. Also, I would like to extend my thanks to the participants for your time and unwearying attention throughout the session. I'm confident that you have learned a lot of things today and hope to see you all in our next events too. So
Yeah.
let's wind up the session, right?
Yeah. So thanks for having me here. And as I said, if any one of you need any help or any guidance or anything throughout your undergraduate years, just reach out through staff or through any means. We'll do our best to help you. Yeah. Cheers. Thank you.
Okay, thank you very much again, Aya. And
Yeah,
have a
no
good
worries.
night.
Yeah. Yeah, you too, I guess. Okay. Bye-bye.
Bye.